welcome to this problem walkthrough. Today, we'll be tackling problem number 491, increasing subsequences. In this session, we'll explore different approaches to solve the problem effectively. Let's dive right in. The problem asks us to find all possible increasing subsequences from a given array of integers, where each subsequence must have at least two elements. An increasing subsequence means that the elements are in non-decreasing order, so duplicate values are allowed as long as they don't disrupt the order. A subsequence itself is formed by removing some or none of the elements from the array, while maintaining the order of the remaining elements. For the input, we're given an array of integers called nums, and the output is a list of lists where each inner list represents a valid increasing subsequence. Importantly, the output does not need to be in any particular order. Any order is acceptable as long as all valid subsequences are included. Let's look at an example to better understand this concept. Suppose the input array is nums equals 4, 6, 7, 7. For the input nums equals 4, 6, 7, 7, the output consists of all valid increasing subsequences with at least two elements. These include 4, 6, 4, 7, and 4, 6, 7, among others. For example, in 4, 6, 7, the sequence remains valid because the numbers are added in increasing order. The subsequence, 4, 6, 7, 7, is also valid because repeated elements like 7 maintain the non-decreasing order. Other subsequences, such as 6, 7, and 6, 7, 7, show how starting from different positions in the array can lead to new valid combinations. Even 7, 7, and 4, 7, 7 are valid because duplicates are allowed as long as the overall order is not disrupted. This example highlights that a variety of subsequences can be derived from the same input, provided they meet the criteria of being non-decreasing and having at least two elements. Now consider another example where the input array is nums equals 4, 4, 3, 2, 1. In this case, the input array nums equals 4, 4, 3, 2, 1 has only one valid increasing subsequence, 4, 4. This is because all other combinations fail to maintain the required non-decreasing order. For instance, sequences like 4, 3, or 3, 1 decrease in value and are therefore invalid. Similarly, combinations involving the numbers 2 or 1 cannot form valid subsequences because their relative order in the array breaks the non-decreasing condition. This example demonstrates that in some cases, the constraints of the problem may limit the number of valid subsequences significantly. Let's look at one more example with the input array nums equals 1, 2, 3. For the input nums equals 1, 2, 3, there are several valid increasing subsequences. These include 1, 2, 1, 3, and 2, 3, which all maintain the non-decreasing order with exactly two elements. The subsequence 1, 2, 3 is also valid as it uses all the elements of the array in increasing order. This example highlights how arrays that are naturally sorted in increasing order can give rise to a larger number of valid subsequences. Now, considering the constraints, the input array can have up to 15 elements, and each number can range from -100 to 100. This means we must ensure that our solution is efficient enough to handle larger arrays. Additionally, edge cases such as arrays with all identical elements, strictly descending arrays, or arrays with only one element need to be accounted for, as these can limit or eliminate the number of valid subsequences. Understanding these constraints ensures our solution is both correct and efficient. To solve the problem of finding all increasing subsequences, we first considered two approaches. The brute force approach involves generating all possible subsequences of the input array using recursion. While this guarantees that we explore all possibilities, the challenge lies in its inefficiency. With an exponential number of subsequences, filtering out those that are not strictly increasing or have fewer than two elements adds significant computational overhead. This makes the brute force method impractical for larger inputs. A more refined approach is optimized backtracking. Here, we build subsequences step by step, ensuring that each addition maintains the increasing order. By using a set, we can efficiently track and eliminate duplicate subsequences. This method leverages the controlled exploration of backtracking, combined with pruning of invalid paths, to significantly reduce redundant computations compared to brute force. Although the worst-case time complexity is still exponential, this strategy is far more efficient in practice. The optimized backtracking approach strikes a good balance between simplicity and efficiency, but using a global set for deduplication can consume a lot of memory. To address this, we refine the solution further by introducing hash-based deduplication. Instead of a global set, we use a local set within each recursive call to track duplicates, ensuring that duplicate elements are avoided at the same level of recursion. This adjustment not only reduces memory usage but also keeps the solution clean and focused. While the time complexity remains the same as the previous backtracking approach, the reduced memory overhead makes this method more practical. Ultimately, we chose the optimized backtracking with hash-based deduplication as our strategy. It offers a clear and intuitive way to incrementally build valid subsequences while efficiently avoiding duplicates. By combining pruning techniques and localized deduplication, this approach minimizes unnecessary computations and memory usage, making it the most balanced solution for the problem. The algorithm follows a systematic backtracking process. First, we define a helper function that takes the current index and the subsequence built so far as parameters. At each step, we iterate over the remaining elements in the array, starting from the current index. A local set is used to track elements already added at this level, ensuring that duplicates are skipped. For each valid element, we append it to the current subsequence, recurse further to explore subsequent possibilities, and then backtrack by removing the last element. This ensures that we explore all valid paths without permanently altering the sequence. We collect all subsequences that meet the criteria of having at least two elements and being strictly increasing. The pseudocode demonstrates how these steps come together. We initialize an empty result list, define the backtracking function, and then invoke it starting from index 0 with an empty path. By maintaining increasing order and avoiding duplicates at each level, we ensure that the generated subsequences are both valid and unique. This algorithm is a robust solution for generating all valid increasing subsequences. By leveraging backtracking, it explores possibilities methodically, pruning invalid paths to save computation time. The use of a local set for deduplication is key to avoiding redundant subsequences while keeping memory usage efficient. Together, these strategies make the algorithm both practical and scalable for typical input sizes, ensuring it handles the problem requirements effectively. To solve the problem of finding all unique, strictly increasing subsequences of an array nums, we start by generating all possible subsequences. This is done using recursion, where at each step, the algorithm decides whether to include or exclude the current element from the subsequence. Think of this as building a decision tree, where each level corresponds to an element in the array. The base case occurs when all elements have been processed, at which point we add the generated subsequence to a collection of results. This exhaustive approach ensures no potential subsequences are missed, even edge cases like empty subsequences. However, generating all subsequences comes at a high computational cost, with a time complexity of 2 to the power of n, where n is the length of the array. This lays the foundation for the next steps, where we refine the results to meet the problem's requirements. Once we have all possible subsequences, we need to filter out the ones that don't meet the problem's criteria. A valid subsequence must have a length of at least 2 and be strictly increasing. To enforce these rules, we iterate through the collection of generated subsequences and use a helper function to check if each one is strictly increasing. Any subsequence that fails either condition is discarded. This ensures that only valid subsequences are considered for the final output. Additionally, we address the issue of duplicates by storing subsequences in a set. By converting each subsequence into a tuple, which is hashable, we take advantage of the set's property of only storing unique elements. This is both efficient and straightforward, as inserting into a set has an average time complexity of 1 per operation. These steps refine the raw results and prepare them for the final output format. After filtering and deduplication, the next step is to convert the set of unique subsequences back into the required output format, which is a list of lists. If the problem specifies, we may also sort the subsequences lexicographically to ensure proper presentation. This final conversion step ensures that the output adheres to the expected format. Recursion plays a key role throughout this process, as it allows us to explore all combinations of elements efficiently without explicitly generating permutations. Using a set for deduplication is both space and time efficient, making it an optimal choice for this problem. Additionally, we handle edge cases, such as an empty input array, which would result in an empty output list, or arrays where all elements are identical, which would produce only one valid subsequence. These considerations ensure the robustness of our solution. The solution relies on two key data structures, sets and lists. Sets are used to store subsequences because they ensure uniqueness, which is crucial for eliminating duplicates efficiently. Lists, on the other hand, are used during the recursive backtracking process to build subsequences dynamically. This is because lists allow us to append and remove elements efficiently as we explore different paths in the decision tree. To illustrate the data flow, consider an input array nums equals 4, 6, 7, 7. During recursion, each element prompts a decision to include or exclude it, creating branches in the decision tree. For example, starting with nums 0 equals 4, we can either include 4 or skip it. This process generates all possible subsequences, such as 4, 6, 4, 6, 7, 6, 7, and more. We then filter out invalid subsequences and remove duplicates, ensuring only strictly increasing subsequences with a length of 2 or more are retained. The result is a set of unique subsequences that meet the problem's requirements, which we convert into the final output format. This algorithm is optimized through several key techniques. Recursive backtracking eliminates the need for manually tracking combinations, which simplifies the code while ensuring all possibilities are explored. Deduplication is handled efficiently by storing subsequences in a set, where duplicates are removed in O(1) time per insertion. Additionally, we can optimize further by implementing early stopping. For example, if the current element is smaller than the last element in the subsequence, we can skip exploring that path entirely, as it would violate the strictly increasing requirement. In terms of complexity, the time complexity is O(2 to the power of n asterisk k, where n is the length of the input array and k is the average length of valid subsequences. The space complexity is O(2 to the power of n, as we may need to store all subsequences in the worst case. Together, these optimizations ensure the solution is both efficient and scalable, even for larger input arrays. This Python implementation solves LeetCode problem number 491, increasing subsequences. The goal is to find all unique, strictly increasing subsequences of the input array nums that have at least 2 elements. We define a solution class with a method findSubsequences. This method uses a backtracking approach to generate all valid subsequences. Here's a detailed breakdown. 1. Helper function backtrack. This recursive function explores all subsequences starting from the given start index and builds a potential subsequence stored in path. If path has more than one element, it is added to a set called result. Using a set ensures that duplicate subsequences are automatically eliminated. The loop runs from start to the end of nums, and for each index, it checks if the current number can be added to the subsequence, i.e., it is greater than or equal to the last number in path. If this condition is satisfied, the function recursively calls itself with the updated path and the next starting index, i+1. 2. Main logic. The result set is initialized to store unique subsequences. The backtrack function is called with a starting index of 0 and an empty path. 3. Return result. Finally, the result set is converted to a list of tuples and returned. This approach ensures that all increasing subsequences are generated, and duplicates are eliminated efficiently using a set. The algorithm is optimized to skip invalid paths early, reducing unnecessary computations. The given problem of finding all unique non-decreasing subsequences with at least 2 elements is solved using a backtracking approach. Here's how the code works. We define a findSubsequences method that takes the input array nums. Inside this method, we declare the backtrack function, which is the core of our solution. The backtrack function takes 2 parameters, start, indicating the index to begin exploring, and path, representing the current subsequence being built. The first step in the backtrack function is to check if the current path has more than one element, a valid subsequence. If it does, we add it to the result set as a tuple. Using a set ensures that we avoid duplicate subsequences automatically. Next, we iterate through the array starting from the start index. For each element, we check if the path is empty or if the current number is greater than or equal to the last element in the path. This ensures the subsequence remains non-decreasing. If the condition is satisfied, we recursively call backtrack, incrementing the start index and appending the current number to path. The result set stores all unique subsequences generated by our backtracking process. Finally, we convert the set to a list and return it. This ensures the output matches the required format. The code handles edge cases like empty input or arrays with all identical elements due to the inherent properties of the backtracking algorithm and the use of a set for uniqueness. The time complexity is exponential, 2 to the power of n, since we explore all subsequences, but the use of pruning in the set helps optimize the solution for practical input sizes. This is the Java implementation of LeetCode problem number 491, non-decreasing subsequences. It mirrors the Python solution by using recursion and backtracking to explore all valid subsequences. The main differences include the use of Java-specific collections like ArrayList and HashSet, as well as explicit type declarations. The findSubsequences method takes an integer array as input and generates all non-decreasing subsequences with a length of at least 2. Backtracking ensures the solution explores every possibility while maintaining the order of elements. We start with the input array nums equals 4, 6, 7, 7, and initialize an empty set named result to store unique subsequences. The backtracking function is initially called with index 0 and an empty path, representing the sequence we are building. In the first call to backtrack, the path is empty, and we loop over the array starting at index 0. At index 0, we add the first element, 4, to the path since it's a valid starting point. This leads to a recursive call of backtrack, now with the updated path, 4, and starting at index 1. In the next recursive call, the path is 4, and we iterate from index 1 onward. At index 1, we encounter 6, which can be added to the path because it's greater than or equal to the last element in the path, 4. This results in another recursive call with the updated path, 4, 6. At this point, the path, 4, 6, is added to the result set. Continuing the loop, at index 2, we add 7 to the path since it's valid, leading to another recursive call with the path updated to 4, 6, 7. This path is also added to the result set. We then proceed to index 3, or another 7 can be added to the path because it's equal to the last element. This gives the path, 4, 6, 7, 7, which is added to the result. Once we reach the end of the array, we backtrack, exploring alternate paths by skipping certain elements. The algorithm systematically backtracks to explore all possible paths, ensuring every valid non-decreasing subsequence is considered. For instance, starting from 4, it also explores paths like 4, 7. Similarly, from 6, it generates sequences such as 6, 7, and 6, 7, 7. By including and excluding different elements, the algorithm builds all valid subsequences. After finishing with the input array, the result set contains all unique subsequences. Converting this set to a list, we get the output 4, 6, 4, 6, 7, 4, 6, 7, 7, 4, 7, 6, 7, 6, 7, 7, 7, 7. Moving on to another example, consider the input nums equals 4, 4, 3, 2. This time, we initialize result as an empty set and call backtrack 0 to explore paths. For the input nums equals 4, 4, 3, 2, the algorithm identifies that only the subsequences 4 and 4, 4 are valid because 3 and 2 are smaller than the prior elements in the path. This yields the result 4, 4. Now, consider the third example with nums equals 1, 2, 3. Here, the algorithm systematically explores all increasing paths, resulting in subsequences like 1, 2, 1, 2, 3, 1, 3, and 2, 3. These paths are added to the result, which gives the final output 1, 2, 1, 2, 3, 1, 3, 2, 3. This demonstrates how the backtracking approach effectively generates all non-decreasing subsequences for different input arrays. To analyze the time complexity of generating all non-decreasing subsequences, we start by observing the number of subsequences we could potentially create. In the worst case, every number in the input list can either be included or excluded from a subsequence, leading to a total of 2 to the power of n possible subsequences, where n is the length of the list. However, since we are only interested in non-decreasing subsequences, a subset of all possible subsequences, the actual number is smaller but can still be quite large in the worst case. Next, let's consider the recursive calls made during backtracking. At the top level of the recursion, the algorithm has a branching factor proportional to n, as it iterates over all elements. This branching factor decreases as we go deeper into the recursion tree, but the total number of recursive calls remains proportional to 2 to the power of n. This exponential growth dominates the time complexity, making it 2 to the power of n. Now, for each valid subsequence generated during our backtracking, we add it to the result set in the form of a tuple. The time taken for this step depends on the length of the current path, which can be at most n. This means converting and adding a single subsequence takes n time in the worst case. When we combine this with the exponential number of recursive calls, the overall time complexity becomes n*2 to the power of n. Shifting to space complexity, there are two main contributors, the recursive stack and the memory used for storing the results. For the recursive stack, the depth of the recursion tree is at most n, which means the stack space required is n. For storing the results, we need to consider that there can be up to 2 to the power of n subsequences, each of which can have a maximum length of n. Therefore, the memory required for the result storage grows as n*2 to the power of n. Combining these factors, the overall space complexity is n*2 to the power of n. To put this in perspective, let's compare it to a brute force approach. A naive method would generate all 2 to the power of n possible subsequences and then filter out the non-decreasing ones. This would involve 2 to the power of n, time for generating and an additional 2 to the power of n*n, time for filtering and storing, resulting in a total time complexity of 2 to the power of n*n. By contrast, the backtracking approach is more efficient because it avoids exploring invalid paths, saving computation time. When analyzing the algorithm's performance under different scenarios, the best case occurs when all elements are identical, reducing the number of subsequences significantly, and the algorithm runs in close to n time. The worst case arises when the input list is strictly increasing, maximizing the number of subsequences and pushing the complexity to n*2 to the power of n. On average, for moderately sized inputs, the time complexity tends to lean closer to the worst case due to the exponential growth in subsequences. Overall, backtracking is an effective way to solve this problem, balancing efficiency within the constraints of its exponential nature. When solving this problem, there are a few common mistakes to watch out for. First, not validating subsequences with the correct constraints can lead to errors. Specifically, you need to ensure that every pair of adjacent elements in your subsequences satisfies the condition that the value at index I is less than or equal to the value at index I plus 1. Failing to enforce this will generate invalid subsequences and produce incorrect results. Another mistake is inefficient handling of large input sizes. Since the total number of subsequences grows exponentially with the size of the input, using brute force for arrays approaching 10,000 elements is computationally infeasible. This can lead to time limit exceeded errors, especially in competitive programming. Finally, off-by-one errors are another trap. Forgetting to check that a subsequence has at least 2 elements can result in including single-element subsequences, which are not valid according to the problem constraints. These are all critical pitfalls to avoid. Another issue to be mindful of is failing to use memoization or dynamic programming in recursive solutions. Without memoization, the same computations may be repeated multiple times, leading to exponential runtime complexity that can make the solution impractical for large inputs. It's also important to handle edge cases correctly. For example, arrays with just one element, arrays where all elements are the same, or arrays sorted in strictly descending order require special consideration. If these cases are overlooked, your program might produce incorrect results or crash unexpectedly. By addressing these issues, you can significantly improve the robustness and efficiency of your solution. In an interview setting, this problem provides a great opportunity to demonstrate key problem-solving skills. One area of focus is pattern recognition, identifying the structure of subsequences and applying techniques like dynamic programming or backtracking to solve the problem effectively. Interviewers may test your ability to recognize overlapping subproblems or optimize a brute force approach. They may also challenge you to evaluate the suboptimality of brute force and refine it with more efficient methods, such as using dynamic programming or binary search. Additionally, edge case testing is a common theme, so you should be ready to handle scenarios like empty arrays, arrays with repeated values, or arrays with only one element. Finally, interviewers often ask about trade-offs. For instance, you might compare the space complexity of a memoized dynamic programming approach with the runtime complexity of a brute force solution. Being able to articulate these trade-offs is a valuable skill. Related problems you may want to review include the longest increasing subsequence problem, the number of longest increasing subsequences, and the largest divisible subset. Now let's consider some alternative approaches to solving this problem. The first is backtracking, where you explore all possible subsequences recursively and filter out the valid ones. While this method is straightforward to implement, it has a computational complexity of 2 to the power of n, which makes it inefficient for large input sizes. A more efficient approach is dynamic programming. Here, you use a DP array where each entry represents the longest non-decreasing subsequence ending at a particular index. This method has a time complexity of n squared, and is a good balance between simplicity and efficiency, though it does require extra space. Finally, for the most optimized approach, you can use dynamic programming combined with binary search. In this method, you maintain an array to store the smallest possible end elements of increasing subsequences of various lengths. Binary search allows you to efficiently update this array, achieving a time complexity of n log n. However, this method can be more challenging to implement and explain within the constraints of an interview. Each of these approaches has its pros and cons, so it's important to choose the one that best fits the problem and context you're working within. Great work! To wrap up, we reviewed the problem, discussed key insights, and highlighted important takeaways. Keep practicing, and don't forget to explore other similar problems to strengthen your skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!